first of all, thank you all for joining. We have 70 minutes. I hope that on one hand it will be enough, but on the other hand, if we go through like the standard program of the presentation and the workshop faster, then hopefully there will be plenty of time for like a proper conversation afterwards. All right, so let me start. So I will start. We will go through a short introduction, then we will refresh some like basics about Apache Iceberg, what it is, and then through various aspects of how Iceberg tables can be optimized and tuned. We will also go through the features of the format as well. And then we will basically summarize it, and then there will be time for Q&A. Now, I will spend a minute speaking about me so that I can introduce myself properly. In the past, I worked, so that's the majority of my data engineering experience. I worked for almost 5 years at Zalando. I was working on its data lake, and I also worked with data scientists, supporting them with like more demanding Spark jobs, essentially like helping them re-implement their calculations in a more scalable manner. Currently, I am a staff data engineer at Gropius, a company based in Vienna and in Berlin. You can find me on LinkedIn, and you can also, if you would like to do that, if you have Orally subscription, you can see my video course on Iceberg that covers slightly different topics that I will cover today. It is available there. My interest in Iceberg essentially started at Zalando. We were considering it, but however, back then the technology was really not that mature, so we just went with Databricks and Delta Lake, which was a good and already reliable alternative. However, I kept that interest, and basically since then I have created several presentations, did my experiments, and also some research for Gropius, essentially around Iceberg as well. So I will present the company in a minute. So essentially, what Gropius does is we are trying to like disrupt how the residential buildings are built. They are made of timber. Our apartments are controlled by smart devices in Bluetooth meshes. The entire value chain is digitized from design to construction. We completely automated generation of walls and elements. So basically, like they are completely auto-generated. And the production of those elements is done by like kind of like car factory style in a factory with like proper robots. What you see below here is a project that we are building currently in Memmingen, and we also have several other projects, including Berlin. So this kind of development requires quite, like in order to digitize it, it requires quite complex data modeling. So we are mixing relational datasets with knowledge graphs, and one of the things that I did as part of that work is I tried to see if we could already use Iceberg and its time traveling capabilities to essentially create virtual graphs on top of that, and then like deploy it effectively. I even submitted like a second submission to Buzzwords, however that one wasn't accepted. So if those topics are also interesting to you, I would be happy to talk about them afterwards. Now, when it comes to rules of engagement, I would, on one hand, we are doing it in a way that looks like a regular presentation. On the other hand, there will be code examples that I will be doing live. And since this is a workshop, I would ask you to actually be like interrupt, ask questions, even like in the middle of whether I'm like doing something. There is a section for like QA at the end. However, I am happy to like interrupt my flow and basically enter a conversation in the middle of it. If you would like to follow the code examples, you could try to set it up. I mean, it's not necessary. If you would like to maybe follow up later after the conference, I am going to be using my repository in which I experiment with Iceberg. The requirements are that because this is a local environment with multiple containers, so you will have to have Docker Compose installed. And if you are on Windows, the Docker has to be configured with WSL2 as its backend. So you have to have the Windows subsystem for Linux installed as well. I myself use Debian instead of the original, I mean the default Ubuntu. However, it should work for both. If you want to do it now, then it will take some time to build, and I can guide you through it, but otherwise I will continue. The stack, so the Docker stack, the Docker Compose stack consists of Minio as storage. So Minio is essentially this S3 compatible storage layer that you can deploy also locally. And I decided to use that because this way, even if the entire thing is run locally, you can get kind of the experience of having it on AWS S3 as if what you used was a object store. Then as the catalog for Iceberg, in this case I use Lakekeeper, which is one of the more recent implementations of Iceberg, of the specification for the Iceberg REST catalog. It's open source, written in Rust, so it's quite performant, and I wanted to use that so that I have basically a pretty good REST catalog implementation at my disposal. There is Spark in the form of PySpark and some libraries like DuckDB, Polars, and PyIceberg for querying the table that we are going to present. And the entire interaction is going to be happening in Jupyter Notebooks. So now, just in case I am going to switch to the code base of that repository and just show you more or less how it works. So in order to run this example, you will have to enter the Iceberg folder and switch to the buzzwords, to the workshop branch. I am going to increase the size of that code base so that you can, of that console, so that you can see it. The stack is already running for me in the other console. Building of it will take some time, unfortunately, because, well, there is plenty of images to be created, and some of them take time. And when it comes to the basic setup, you will see the definitions of Docker images in here. So the Jupyter image contains all the libraries that we are going to be using for interaction, and that includes PySpark, which conveniently installs Spark as well. So basically, within a single container, we can have both Jupyter and a single node Spark, which is fine for local experimentations. Then we have Lakekeeper here. So the setup of the Lakekeeper can be pretty tricky at the beginning. Essentially, what is happening here is that there is one service just for the Lakekeeper, and then there is the first step in which we are doing certain a setup basically of that environment. All of that because Lakekeeper needs to be initialized. Now all of that is described here in the README. So I hope you will not have any issues following it. But again, if so, I'm happy to help out. All right. So let's start with a quick refresher on Apache Iceberg. So the main features, right? So first of all, Apache Iceberg is a open source format that has completely open specification under the Apache Foundation. which means that everybody is fully free to provide implementations, of which there are already several. It offers the specification is designed in a way that offers full ACID properties, so atomicity, consistency, isolation, of which we are going to be talking more later, and also durability. Then we have so-called time travel, which means essentially free movement across table history through the data snapshots. Flexible schema evolution with arbitrarily nested columns, free removal and addition of that. So-called hidden partitioning, which is, I think, one of the most interesting features of Iceberg, and we are going to spend some time working with it. Which can, but essentially hidden, like one of the most important aspects of hidden partitioning is that you can use projections of function values based on values of the column to actually project the value of the partition. When I say that Iceberg is multi-engine and multi-storage, that just means that you can deploy it essentially anywhere on the cloud, on HDFS, on any local storage with local volumes as well. Multi-engine, that just means that there are multiple data processing engines and libraries that already support it. Although I would say that Spark is always like the safest choice here because the implementation of Spark runtime for Iceberg or Iceberg runtime for Spark is part of the official code repository of Iceberg, and for this reason, the let's say feature support there is like the best. And then there is a lot of metadata exposed that it can be used for query optimization by the engines, but also for exploration of what is going on with any particular table, and we are going to go through that as well. A deployment of Apache Iceberg includes three components. So in general, there is no such thing as like downloading Iceberg. You cannot just download it as a service. You have to compose a environment that can like speak it, so to say. So for that, you need like storage for data and metadata files, and this can be like in the cloud. It can be Google Cloud Storage. It can be AWS S3. It can be Azure Blob Storage as well. Processing any like kind of processing engines from Spark to even like DuckDB is going to work with Iceberg, although with let's say diverse support for its features. And like a central element of that deployment is also a catalog, because while the metadata mostly resides on the storage, the catalog is actually registering the tables and is responsible for like an atomic swap on when a transaction is committing. So it keeps pointers to the recent metadata file, and it is essentially the transaction manager for Iceberg tables as well. The default table layout, or like if we look at the table like in general, so at the top again we have the catalog with the pointer to the latest metadata file. Then we have 3 layers of metadata, which are stored, like collocated with the data by default under table location /metadata. However, this can be configured. Like you can store your metadata in a completely different location than the data. Then by default, data is stored in the table location /data. The metadata itself, again, has 3 layers, so-called metadata files, then manifest list files, and then manifest files. The first of them, so the top layer, the metadata files, they are stored as JSON. They point to the manifest list, basically to the manifest list that represents a snapshot of the most recent snapshot, or its particular snapshot of a table, and carries certain structural information about a table. Its schema definition, its partition layout, and also the list of past snapshots. Then a manifest list file will be stored as Avro. Actually, it's structured as if it was on its own like a correct Iceberg table, and there is, like, for a single snapshot, there is a single manifest list file, and like this file points to manifest files that represent like individual data files. So this is where the tracking, so manifest files, the like, let's say bottommost layer of metadata in Iceberg is responsible for tracking individual data files. Each data file in an Iceberg table across snapshots, across its history, is tracked individually in the metadata. And there is essentially no operation on the data files or like data file discovery for Iceberg readers or writers does not involve a listing, which is one of the most important points when it comes to performance in query planning. All right, so now I am going to go to my notebook environment and start running some code. So the first thing I will do is that I am going to make sure that I have a S3 or like Minio S3 bucket available. Now this should be actually already there, which is the case. So there is an error, which means that basically the bucket already exists. But if you run it for the first time, it will create that bucket on Mini.io. Then what we have to do, we have to bootstrap the catalog. And again, in my case, you can already see that the catalog is already bootstrapped. But this is a step that is required, like the first time you deploy at least Lakekeeper. So those procedures for managing catalogs are individual per catalog implementation. So this is not going to be universal. And then we are going to initialize the Iceberg warehouse in Lakekeeper. And in that case, I also have this catalog already, so the response from the catalog is telling me exactly that. What is maybe interesting to notice here is that since the catalog is, Lakekeeper is a implementation of the REST specification, the REST catalog specification, you can essentially do everything you would do with an Iceberg catalog using just like a basic HTTP library of your language, programming language of choice. In my case, since I'm using Python, it's requests, so I am just performing those requests with that library and can interact with the catalog. And then let's check what the config of that warehouse is. So there you go. That's the response. There is some information here, effectively showing us what endpoints we have in that catalog. And what is important here is that those endpoints here, contrary to the management endpoints that you saw previously, those endpoints, they are actually part of the catalog, REST catalog specification for Iceberg. So every REST catalog for Iceberg is going to be implementing an API that is formulated in this way. All right, so the next step I will do is I will make sure that the Spark client works. And in this case, actually, I have one extra that I don't need. I'm going to just a second. Yes, I am going to remove the Nessie ones because that was from a different experiment. Please excuse me. Basically, the only thing, because I wanted to make sure to drive this point, is that Iceberg Spark session extensions. It's an additional jar that you can install with your Spark. It's very useful, basically, for all the table management operations using Spark that go outside of the standard Spark SQL dialect. Essentially, there are some system procedures that we are going to be running that are required by that are provided by this particular package. And if you would like to see how it could be deployed, in the definition of the Docker image for Jupyter, where the Spark is also contained, there are those lines essentially that point to particular jars that are required in my environment, which means Iceberg with particular Spark, with extensions, and with S3 or with S3 compatible storage layer. Again, so let's run it again and show exactly. So we are trying to list the namespaces from the Iceberg catalog. However, there are no namespaces defined yet, so the result is basically empty. And the general conventions that I am going to use is I am going to use basically conversion to a pandas data frame for each Spark SQL command so that they are like nicely formatted. Now, the next thing that I am going to do is I am going to check the existence of the .py iceberg YAML file, which actually defines the catalogs for PyIceberg, which is the official low-level Iceberg implementation for Python that doesn't involve any additional dependencies apart from, it doesn't require an additional query engine, let's say like Spark. And in order to show you what it is, what it looks like, in this case, I'm just configuring the catalog that I call REST, and then like the familiar options that are required for this setup are here. And then we can check whether we can actually use PyIceberg instead of doing it through Spark SQL to create a namespace called workshop in which we are going to be working. So there you go. Just by using PyIceberg, we have created a namespace in that catalog. And when we list those namespaces, we actually get the response with the workshop existing. So the next step that we are going to perform is a simple table definition. And in that case, so first of all, I am going to drop it just in case. So this is just a cleanup if this already existed. And the table is going to consist of 4 columns, an ID that is going to be a string because we are going to generate it using UIDs, just to have basically a random string there. Then there will be a name that we are going to just, a name of a person, for example. We are going to randomly pick it from a short list. Then there will be some integer value, and then there will be some timestamp. And this is all just for presentations. Basically, I wanted to cover the most important data types here. So the table and the table is going to be partitioned, and this is where we are already getting into the partitioning. It's going to be actually partitioned by years transform of the timestamp. And then the only property that I am going to set here is that I am going to set the Iceberg format version to 2, which is the most widely supported currently. We are technically already at version 3 with some additional data types and improvements to the storage layer. However, I would say that version 2 is still the safest in terms of compatibility. And then since we have defined this table, we can actually already try to describe it and see what we can learn about it. So this is a pandas data frame describing it. We have the column names, and then we have the partitioning described here. There are some metadata columns as well, which we may actually... so this is something that we may actually use later, basically experiment on them as well. And then we have some detailed table information. But this is this is stored in catalog, and it's kind of catalog specific. So now we are going to be, what I'm going to do is insert some data, and instead of using Spark SQL, I'm going to use the data frame API of Spark, just so that, because it is just easier for me to make it look more structured and also do this insertion with random values. So we are going to be, we have 4 available names: Ariel, Georgina, Tom, and Ulma. I am also going to be inserting 2 different timestamps, and then I am also going to from 2 different years. And I am going to add like an ID that is just a UID4, essentially, so that like gives us a unique value. We can run it actually several times. I mean, there is no harm in that. So there will be several inserts. And now if we select everything from that table, we can see that we have 6 entries. This is the ID, the name, value, and the timestamp. The values are random as well. So, excuse me. So we have like a basic table that we can work with, and we can already we could actually make an experiment that to see if we can also get some metadata columns working. So let's see. This is something I haven't tried. So let's see if it works. And there you go. So as you can see, so this is a like very interesting aspect of Iceberg. Basically, for each, apart from all the data columns, I have also selected for the metadata column _ file, and this way I am getting actually the detailed information about which data file contains that particular row, which is very useful for tracking, for example, data lineage, right? So you can do it. Just with a simple query. Let's do more then. Let's actually also query for the partition, because why not? And then exactly, we can see that this is, so here we have partition values. As a reminder, we have only one partition here, I mean one partition column that is using the years transform. Now, a caveat here is that the years transform is counting the years from the 0 Unix timestamps from 1970. And this is why it's 54 or 55, because we inserted 2024 or 2025. All right, and then we can start also querying right away the history of that table. So the history is going to show us basically the snapshots. And just a reminder, I have performed this insert 3 times, so we have 3 snapshots, each representing the table at a different stage. And we can also, for example, query some columns from as a warm-up from the data files metadata table. So you can see that basically you can query metadata tables by just adding a dot and then the name of the metadata table as well to inspect the table. And then you get, for example, in this case, like a list of data files, the count of records for each data file, and then the partition in which this file is stored. All right, so before we go into the partitioning related code, I am going to switch back to the slides, because there is some like introductory information I would like to go through. So basically now we are going to go through like several aspects of optimization of Iceberg. Now, what this actually means depends on the context, because optimization can be multi-dimensional. Usually when we are talking about datasets or tables, you can think about optimizing your table for read queries, for data modification queries, but also maybe for storage size. There are other aspects that we could optimize for, like, for example, data recency, consistency. Like, again, that really depends on a particular use case and a particular situation. So the partition layout. So in Iceberg, partitioning doesn't rely on folders like in Hive. Essentially, files can be distributed. So by default, they are going to be laid in like folders that depend on the partition values. However, this is not something that Iceberg requires, because you can essentially configure Iceberg with multiple custom location providers, and then you can like kind of direct it to store data files as you wish when it comes to the data paths. Now, the assignment of each data file to a partition is explicitly tracked in the metadata, so in the metadata files. So again, since we cannot even rely on the physical structure of the table. There is no other way for a reader to discover to which partition a file belongs, and therefore we have it in the metadata, which also speeds up like querying for a particular partition value. And a single data file can belong only to a single partition. And that means that if we are talking about partitioning by multiple columns, then a single file will be can belong only to one unique combination of values of each partition column. There is a flip side to that I actually didn't mention here, is that means that actually partitioning in Iceberg is not hierarchical like in Hive. It's just that you get it's more like assignment by coordinates, right? So basically, like partitions have, you could say, coordinates where each dimension. So for each partitioning attribute, you get like a new dimension for those coordinates, and then the value in that the partition value for that file is identifying it in this like space of possible partitions, which makes it kind of work like a bit like an index. Now, columns can be added and removed from the partition layout freely, and this includes nested columns. And this is one of the most interesting aspects of evolution of an Iceberg table, is that if we modify a partitioning layout, it's going to be applied to the data files moving forward, and the data files that are already there are going to still be stored with partition values corresponding to the previous partitioning layout. We will actually see it on code examples. Now, partitioning can be defined like we already did also on transforms. So those transforms are available for Iceberg version 2. So you get like those basic transforms for datetime columns, but also there is nice hash-based bucketing. So you can basically say that you want to create a partition value on a particular column, bucketed into one of n buckets, right? And it's going to be like attempting to make to do like uniformly distributed bucketing through this hash function of those values. This is like a nice thing to for example, do with a high cardinality columns, if you would still like to have some kind of a grouping that is also predictable, because it never goes, in this case, above this like preset n of buckets. And truncate is just truncating like a string. So if you have a string column, you can just like basically do truncating, like project a partition value that takes the first two characters basically of that particular column, and then and that's it. All right. So again, code base and Jupyter Notebooks. Exactly. So what we are going to do now is that I am going to drop the partition field years timestamp. Actually, I could do it with 2 pandas as well, so that the result of the data frame is also visible. And then I am going to do bucketing on the ID field. So those UUIDs, random UUIDs that we use for creating the IDs of each row are going to be thrown into one of 2 buckets. And then I can again describe the table, and now we can see that in the partitioning we just have the bucket 2 of the ID column, so 2 buckets of the ID column. So has there anything changed if we list the data files now, right? Because we haven't yet written anything with this new partitioning scheme. So what happened to our previous files? So now what you see is that the partition becomes the value of the previous partitioning scheme plus none. And the none is, so essentially the partition, as the partition layout evolves, becomes a superset of all partitioning columns over the whole history of the table. So like a sum of all the projected partition columns, and then for those with which a particular file like wasn't partitioned at a given moment in the life cycle of the table are just going to have like the null values there, right? So they will have no coordinate along that partitioning dimension. So we can write more data now to that table with the new partitioning scheme. Again, I will do it like maybe 3 times. And now let's say what the data files are actually showing us. Exactly. So now we have more data files. We have inserted 6 records, and they are distributed across the data files with like 2 records, 2 records, 1 record, and 1 record. And you can see that the old files show the partitioning values of the old partitioning scheme, and the new files are showing the buckets they are in now by the ID column. Conversely, they do not have any partitioning value for the years of the timestamp column, because that column doesn't exist in the current partitioning scheme anymore. We can list partitions of the table, and in here we like for each partition value combination we get some nice metadata with so the specification ID is basically the ID of the partition specification, right? So the first one was the 0, and then we altered the specification twice. We removed the years column, we added the bucket of the ID column, and now we have, so now we are on the third specification, 0 indexed number 2. There is some nice like meta information about this each partition, including last snapshot, data snapshot on which it was created. So this is like more or less how partitioning works. In Iceberg, we can actually still like spend some time talking about it. The advantages of like using partitioning for kind of additional indexing is that you can like increase the file skipping during read queries. Because do you have a question, by the way?
Yeah, maybe finish your.
Okay. Okay, sure. So essentially, what you can you can kind of use it as indexing, because since each partition value is stored in the metadata, you can the reader can, especially for queries with like equi filters, so like where particular, if we want to filter out or like search for rows with particular partition value, it is easier to find them just by the metadata of the partitions. However, and then we can actually extend this pattern, because we can project multiple partition values from one column, so we don't even have to like generate columns, additional columns for additional partitions. However, there is a caveat here, is that because one data file has only like assignment to only single partition, it is going to increase the fragmentation of the data layer among data files, right? Because like without partitioning at all, we can have like a nice table with let's say like large Parquet files, for example. But then if we start partitioning it, those files, like the incoming files are going to be potentially smaller, because each file can only fit one partition, one particular partition, or like combination of partition values. Maybe we could go to the question now.
Yeah. Cool. Yeah, my question was going into the direction of fragmentation and
Yes.
And the consequences for queries. So, given you have a partitioning and it's all good, and your queries use that partitioning, then it's all good. I mean, if you change it, then all new data will be partitioned in a new way.
Yes.
But then when you query, you can only use one of the partitionings, right? Or well, I mean, you could use both, but then parts of the data still have to be scanned fully, right?
Well, not really. I mean, yes and no. Because on one hand, yes, the partition value cannot be used now to discover, like some of those files are not going to be discovered through that filter. However, there are many more things in the metadata of Iceberg, like column ranges and so on, that can still be used for file skipping. But yes, the file skipping is going to be reduced, yes.
Yeah, so it has to touch more files, right?
Yes.
Resulting, for instance, in more like S3 gets and all this stuff, right? So this is what I was referring to. And is there a way of optimizing, like tooling?
Well, like we have to, I think, consider that Iceberg is also designed for tables that are really long running, for years, for example, right? And that means that yes, it is flexible in terms of how you can evolve it, but then you will have older snapshots that don't conform to certain specifications. However, there is always file, like you can always rewrite that table, which is a super heavy operation, but it is going to be happening with the new partitioning scheme, right? And you will like get a new snapshot that is rewritten according to a new partitioning scheme. It may take days if your table is large, but you can do it. Again, it's a tool, right? So you are right. Evolution basically allows you to evolution of partitioning scheme allows you to like kind of gracefully and gracefully and in a very lightweight manner to evolve the partition scheme. But that means that older snapshots or like parts of the table may not be optimized towards your current query patterns.
Okay, so summarized, that would be like, it can be done, but maybe it shouldn't be done too often. Something like that, right? Because I mean, if you have a really big table and like rewriting, it's going to cost you a lot of money.
Yes, absolutely.
And so well, I guess you still need to think about it.
Absolutely. So I would literally think about it as like reindexing plus rewrite, right? So every time you use like partition evolution, you have to take it into account. Although it's just that the possibility is there, right? So like you have the freedom to do that, but like with all the consequences. All right, now. The next thing I wanted to talk about is snapshot management. And in this case, we have and like kind of time travel as well. So basically, snapshots are created in Iceberg tables every time we change something in the data, not the metadata. So for example, metadata operation like evolution of the schema or partitioning layout does not create a new snapshot. It just creates a new metadata file and a new version of the table. However, at the latest data snapshot. So each transaction, each committed transaction is creating a new data transaction, is creating a snapshot. Past snapshots can be queried by snapshot ID or date, and snapshots can be also tagged. So the nice thing about tagging is that you can query them as like kind of separate tables, but also they have completely like a separate retention policy. So if you want to clean up your table and let's say retire older snapshots from the history because you no longer need them, the tags are going to be actually preserved. So you have to explicitly drop a tag in order to clean them up. So they are safe. You can like create kind of in the table history. You can create like a checkpoints essentially from time to time for older snapshots if you need them in your workflow. Again, snapshots can be expired using the expire snapshots system procedure, and I think we are going to actually try to do that now. So first of all, let's list the snapshots of the table that we have already, and excuse me, this is the partitions. I'm lost. Here. So snapshot ID and committed add. So this is basically what I mean. I selected just those two columns, but if we look into the snapshot table, it contains many more. And actually, the summary is very interesting. So let's select it. Because for each snapshot you get like things like how many partitions were changed and equality delays. Like there is a lot you can learn about each snapshot from each entry. And then we can actually we had let me select the snapshot ID again because we will need it. So we have those snapshots are ordered by committed add. So the most recent snapshot is at the bottom, and I am going to query one of those snapshots. Let's say the first snapshot. I suspect it should have 2 entries, and it actually does. So this is our first insert. So this way we basically just like queried the first snapshot after the first transaction of the table. And then it is also possible to query metadata of past snapshots. So if you would like to discover the data files that belong just to that snapshot, I mean, they can belong to multiple snapshots, but if you want to focus on a particular snapshot, you can do it as well. So in this case, we have only 2 data files, each data file consisting of a single row. We can also, so let's create a tag here. Actually, we will again take the first snapshot. The tag is going to be called tag1, and we can first of all we have another metadata table that we can use to query to get all the references, which is like I mean tagging and tags and branches of that table, and we can see that our tag is here, right, and the main branch over which we are also moving along. And then we have Spark, so query that is actually querying that snapshot like a sub table, right? So you can, if you have a tag1 tag, you can like do like tag underscore tag name and then query it as well, which is very cool because then you can start doing like deep joins across snapshots, for example, to like do again, like you can do lineage, you can do auditing of each transaction and so on. And then what we can also do is we can expire a snapshot. So let's expire one snapshot like this one, and I am going to do it just by like the ID of the snapshot. And let's see if this actually expired it. I think it did, because now we have 5 snapshots and we should have 6. So basically the snapshot is gone from the history. Those values here are just big integers. This is why Pandas is displaying them this way, because those should be just snapshot IDs. So we basically kind of overwritten the history of the table and removed one snapshot from it. All right, the next step is libraries. So apart from like large query engines, you can use lightweight libraries to query Iceberg. And in this case, the Python ecosystem is very nice to interact with it. Because on one hand, we can use DuckDB to query Iceberg tables, although only on particular snapshot. We can use Polars, which is this like Rust-based, very fast, lazily evaluated data frame library that I basically by now use completely. Like I replaced my Pandas experiments with Polars completely, and then we have. And then we have also PyIceberg, which is the official implementation that can be like combined with the tool to also work with Iceberg. I will show you how this works. So first of all, I am going to let's start with Polars. I am going to just like configure it. And then. Oh, excuse me, because I think I'm missing I think I'm actually. No, it's good. It's all good. So basically, since we have the table, our table already as the. So here, so just a reminder, we still have this catalog Python object, which represents the catalog in the PyIceberg that we loaded earlier to where we were manipulating the warehouses. And I am loading our table, and then I am setting some storage options for Polars so that it can read from S3 or from Minio actually. And then I am, because what Polars needs is it needs the location, the metadata location of the latest or any metadata file of Iceberg, right? So we are going for the latest one, and we are providing it here. And then with those storage options, we are initiating Polars. And now, what is interesting about Polars is that if you define like a variable with this name, you can then use it as with like a SQL as the table name. So there you go. Apart from some warnings, we have actually a nice output from Polars here. And what is interesting about Polars is that before we do actual querying, it kind of, in terms of evaluation, works like Spark, so it's going to be evaluated lazily, which means that for large data sets, we are not going to just like eagerly load, let's say, terabytes of data for no reason. And this can be seen here. Basically, if we do explain on that statement, it is just going to show us the query plan, right? So we can even do without explain, and then just check the type, and this is just a lazy, so-called lazy frame, so nothing is evaluated unless we actually want to gather the results of the query. Then what we can do is also query Iceberg with DuckDB, and for that, there is a bit of a setup because we need 2 extensions for S3 and the Iceberg extension. So we need one for HTTP file system and one for Iceberg, and then we need to configure it with similar properties. So we are going to do it now. And then basically we can use again the table metadata location and the function Iceberg scan in DuckDB to query that table. And this way we are querying the same table with DuckDB. So we can also do some exploration with PyIceberg. There is this in PyIceberg. There is this object inspect, and it has multiple methods that, among other things, allow us to inspect all these metadata aspects of the table, the way we did that also in Spark. And if we do it for the references, for example, which we already did, we can see kind of the same result as we had from PySpark, is that we have those tag 1 and the main branch here mentioned. Okay, so let me speed up a bit. Let's go to the, well, excuse me, one more thing that I wanted to mention. Is it worth to actually do anything with Iceberg outside of a large engine like Spark? I would say absolutely. So first of all, metadata operations, especially with REST catalog, just you can use any basic library, and then you can do some very lightweight querying on within in-process querying, basically, especially if you know that even if you scan a large data set, the results are going to be small. So you can build applications around it, essentially, that use Iceberg without involving a large Spark cluster, for example. All right, copy on write versus merge on read. So this is a large one. I think, because I think we have only 20 minutes left. So I'm going to go through this pretty fast, but this is a very important aspect of Iceberg. Basically, data files in Iceberg are never rewritten in place, right? So if there is a data modification, there is going to be a potentially new file or more added. And some of the data files may be removed from the table, but by removal, it just means that they are no longer going to be tracked for the new snapshot through the metadata file. So they are going to be still stored on the storage and then accessible to previous snapshots. And then we have four basic operations that modify data. So basically, insert is append only; it only adds files. Then delete can cause a removal of a file and addition of one or more, because it can do it in 2 ways. So we will talk about it. Then we have updates that are essentially inserts plus deletes, and then merge, which is a more fancy update that can involve additional inserts, or we can call it upserts as well, if we are basically making sure that something is there if it isn't, after the query. Which means that apart from insert, all three remaining operations involve deleting. And deleting is actually important to the discussion of copy on write versus merge on read. So I am going to skip that particular section. I am just going to go through the principles. So basically, with the way copy on write works is that it works only on data files. So every time you modify the data, a data file can be removed or not from the table, and then more files can be added. Merge on read works completely different, because instead of, if there is a delete, the file in which the deleted data exists stays in the table, but a small delete file is added to the data files of the table, which means that this is a much more lightweight delete. So in that delete file, it just mentions that in this particular data file, those positions are no longer part of the table. So it is like marking rows for deletion. Leaves the original files and intact. This can be configured by separately by the type of the operation, and the default value is copy on write. Now, where do we pick which one? Essentially, copy on write is optimized for reads. Why? Because the reader doesn't have to merge information from the data files and delete files in order to figure out which data is still there. And it also compacts, makes data compaction down the line slightly simpler. Merge on read, on the other hand, is better for workloads that involve, let's say, much more writing, and we want to have high density of write operations that are kind of lightweight, and then we don't want them to be rewriting data files, right? So instead, they are just going to be dropping delete files. That is just faster to do. However, in this case, we get this side effect of longer read times if we are doing select from that particular table. Compaction is dealing with fragmentation of the data files. So basically, the issue with having more data files is that not only the scanning is slower, but also there is much more metadata in the table, which means that there is also much more I/O involved in every query. And files can be compacted basically with in other. So there is a nice implementation in Spark of for rewriting of the data and delete files into larger chunks that are better to skip over and also faster to read. Now, compaction can be costly because if it is done in a single transaction, it may the compaction job can take hours or days if the table is large. However, compaction can also be done selectively. It's possible to just provide a parameter in which only files are going to be compacted if they consist data according to a particular predicate. And I would say that it has to be kind of scheduled with other workloads in mind. Why? Because while compaction is transactional, so it is just yet another data modification operation. If it interferes with other operations, it may fail. It will be graceful, but you will have to repeat it basically. Metadata compaction is something that can be also done. So basically, manifest files can be rewritten. Now, an aspect of rewriting of metadata of data files in Iceberg is that the rewrite can also sort data within data files, which will just make especially range queries much faster. And this can be also expanded to Z ordering, which is this multi-dimensional clustering of data files. I won't have time to speak deeper about it, but if you have never used Z ordering in your workloads, we can discuss it afterwards to in detail what it does. Then the monitoring of an Iceberg metadata of the Iceberg table can be done nicely through the information in the metadata tables, right? So you can do things like detection of partition imbalances. You can do check the frequencies and the sizes of the commits and the distribution of file sizes of the data to decide whether which part of the table you would like to compact. Find maybe some data anomalies using column ranges as well. All of this is purely metadata based. And we can actually still show some examples. So I will skip over this because this is the last section with code. So again, we could do that with PySpark, but let's do it with Spark. There are some more interesting tables here. So all of these are metadata tables that are available through Spark. And there are also those special ones with all data files, all entries, and all manifests. And the difference between all the data files and files is that files will show you files for a particular snapshot, by default the newest one. But all the data files is going to show you all data files within that table regardless of the snapshot, which we can actually, try out. Yeah, so those are basically all data files that we have inserted into that table. And if we started like deleting data, then there would be even more of them because some of them would be removed and maybe new ones would be added, right? We can go through, again, through partitions we have already gone. Metadata log entries is also like quite interesting. Again, those are going to be showing the files of the metadata. And you can see that for some of them, we don't have like the latest snapshot ID. I think in that case, this means that this is just a progression that happened only because of the metadata operation. Now, we could do more with this, but in general, if you would like to construct more elaborate queries over Iceberg metadata, you can do it usually by joining the snapshot ID. So basically, many of those tables contain snapshot ID, and if you start joining those tables, you can do quite a lot in terms of figuring out what is going on. All right, there is still some aspect that I would like to discuss. So if I were to pick one aspect, I would like to pick isolation levels. So isolation is about the I in ACID, which means that there is, so essentially, if there are two concurrently running transactions, the transaction manager is going to try to figure out whether they can be actually applied in a way that doesn't conflict. And if they cannot, it will fail. The ones that are failing are going to be failing gracefully, so they will not leave the table in a corrupted state. And what is important about Iceberg is that it offers two levels, serializable and snapshot isolation. There is a large difference between them, but basically serializable is full isolation. Snapshot is like a lower level that on one hand allows certain concurrency effects to appear, but on the other hand, it's much more performant because it doesn't require aggressive locking the way serializable does. Serializable is so expensive because it guarantees that if all concurrent transactions at this level succeed, then the table will look like as if they were actually executed in a certain order, which means that the concurrency effects are completely gone and the isolation between them between transactions is complete. And this is an example of like what the difference can be. So if we start with a data set that consists of like 4 rows, blue, red, red, blue, and the transaction 1 flips blue to red, and transaction 2 flips red to blue, if you have snapshot isolation, both transactions start with the same snapshot and write modifications according to what they see at that snapshot, right? Transaction 1 flips those blues to red, and transaction 2 flips those reds to blue, and in that case, we are like ending up with this data set. However, if we do serializable isolation, we get one of those results depending on like which transaction kind of succeeded earlier, so remember that they are executed as if they were executed in order. So the first one is flipping like let's say the transaction 1 won, so all blues are now red, and then the other transaction comes in and sees that everything is red, so it flips it to blue. So in this case, so the choice of the isolation level has not only impact on performance but also on the behavior of the data modification queries. This is a very deep topic. I love it, but again, it would require a separate session to properly cover. Isolation levels can be also set up per type of data modification operation. All right. One more aspect, I think I would say that what is interesting actually, like the last topic that I will cover is Bloom filters. So when it comes to optimizing the tables for reads, especially, we can actually direct at least Spark to write Bloom filters for in Parquet and in ORC for each column individually. And Bloom filters are data structures that are basically doing hashing of the entire row group in a Parquet file. And what they do is that they have no false negatives. So if a Bloom filter tells you that a certain value doesn't exist, it is always right, 100%. However, it has a flip side. If it tells you that a particular value exists, it can be a false positive because of the compression through hashing, the way it works. So Bloom filters are in particular, if you write them to Parquet files and the reader of those files, like Spark, can actually take advantage of them, they are going to be very useful for negative queries, for example. So every query that filters for something not existing is going to be impacted when it comes to performance. When it comes to filters for something existing, is going to be probabilistic, but the probability of false positives can be tuned and also is very low. It's just a helpful additional way to index data. All right. So when it comes to further reading, I can basically recommend diving into the documentation of Iceberg. The Iceberg book from Orally is also pretty cool. I mean, it gets outdated pretty fast because the format develops very fast as well. But it does have certain, I would say, universal aspects to it that are always worth looking into. And with that, we still have a couple of minutes. If there are any more questions, I would like to take them. I would, also be, of course, happy to take them afterwards. All right, yes?
Hello. I had a question on Bloom filters.
Yes.
If I understand them right, they're still written as part of Parquet file itself, yeah? So even if the Bloom filters are saying that there are no values that we need in that Parquet file, the scan still has to read it first to read the Bloom filter itself,
yes.
Or it just can stop at reading the header of the file and not the whole?
Well, it has to. I think a Bloom filter is stored per each row group, I think, for a particular column. And then it can say, okay, is this particular value there or not in this row group? So at least it can do some skipping, right, within a file. It's I would say that Bloom filters are kind of the last line of defense when it comes to optimizing queries, because it already goes into the, if the query optimization is already happening on the data level, that means that the execution went through all the optimization levels happening on the metadata, right? So I would say they are a nice optimization for larger files, for columns that have high cardinality, basically.
So what does it actually save? Does it need to transfer the whole Parquet file over to the Spark node, for example, to apply the Bloom filters, or it can do range reads over S3 to... It
can basically, for a particular part of the Parquet file, determine quickly whether a particular value is there or whether it can move on to the next part of that file. So it can then so something that still couldn't be figured out by things like maybe column ranges, because column range doesn't tell you whether a value exists or not inside. It can still do that skipping, right? It's just an additional thing. It doesn't have to do full scan of that part of the file, at least.
Okay, thank you.
And it's not available in Avro, unfortunately. This is only available in Parquet and in ORC.
Yeah, it's part of Parquet spec itself, not part of Iceberg spec.
Okay,
Is it?
I don't think so. So Parquet is the default in Iceberg, but it's one of the. I wouldn't call it part of the specification of Iceberg, I think.
No, I mean the Bloom filter is specified as part of Parquet specification itself,
yes.
not part of Iceberg.
Excuse me. Yes, I misunderstood. Yes, so Bloom filters are part of Parquet, and then can be then exploited by the readers and by the writers. Yes.
Thank you.
Mihai, thank you very much.
Thank you very much for the audience.
A round of applause.